Okay, so where we ended up with is discussing the semantics of determinism. And if you remember, what we basically found out that under determinism, there would be one-to-one mapping between the rows of the factor and or the complete instantiations of our variables and the subcircuits. And we saw how this makes it clear why the algorithm from 2006 for MPE that we talked about works in this particular case, and why it may break when you don't have determinism. And the theorem here is that if the we're talking about an arithmetic circuit that computes a factor, and if it happens to be also smooth, decomposable, and deterministic, then it can be used to compute the MPE by evaluating the maximizer circuit that we described. That is where you replace addition nodes by maximization nodes. So we just have a few more observations on this segment, which is what else happens when you drop determinism or not drop determinism. That is the difference between deterministic and non-deterministic ACs. And you will see three observations on this front. One is what we call a separation result, parametric incompleteness, and then this mystery that we alluded to at the beginning. So what is a separation result? Well, let me read it to you. There is a family of factors with poly-size, decomposable, and smooth ACs, but exponential size ACs if they're also deterministic. So here's a factor, a family of them. A family means I can make them as big as I want in terms of the number of variables. And I tell you, I want a circuit that computes the factor that's also decomposable and deterministic, decomposable and smooth. And then I want to see what happens if I insist on determinism or not. And in this case, for this family, basically you can find an efficient small circuit that computes the factor and that is decomposable and smooth. But if you insist on determinism, it will blow up, right? So this is what we call a separation result, an exponential separation result. So that's pretty interesting. That's the case. So sometimes you can be more efficient if you just do decomposability and smoothness without determinism. So this is, in a sense, a positive result on gain that I get by relaxing determinism. Parametric incompleteness, what does that mean? If you look at the treatment we gave to the class of arithmetic circuits that are deterministic, we took the graphical model like a Bayesian network. We wrote some things. We did some computation, got back a circuit. And the parameters of that circuit, right, the thetas, were all coming from the Bayesian network. Implicit in that method that we did, that construction method, is that you can always find an arithmetic circuit for this distribution or this factor where the parameters of that circuit come from these tables. Okay. Interestingly enough, that stops being the case if you don't have determinism. If I tell you I just want a circuit that is decomposable and smooth but not deterministic, there is no guarantee at that point that that circuit will have its parameters exclusively coming from the Bayesian network. What does that mean? They have to search for parameters. Okay, that ends up having its own complications. So in a sense, you can think about it, oh yeah, if I relax determinism, then maybe I'll get a smaller circuit. But you get the hit somewhere else. Now you have to work harder to get that circuit, right? Because you can no longer guarantee, it's not just about the structure, you have to also search for parameters. It's a very interesting result. You can look it up if you want to read more about it in the paper. So let me just close on this observation, last observation. And by the way, I should say that what makes this particularly interesting also is that there have been several compilation methods for circuits over the many years, and they're all directed towards deterministic ones and under the assumption that my parameters come from the models. We actually don't have compilation methods that are only ensure the composability and smoothness, that takes advantage of the separation result. The methods that we have are not oriented towards that. We would need a new class of compilation algorithms to take advantage of dropping determinism. So this is actually an interesting research area. The last observation is basically this, what we call a mystery. Now, you know that MPE is NP complete, and computing marginal is PP complete. The class NP is contained in PP. So, right? Yet, the composable and smooth ACs, they allow me to do marginals in linear time, but MPE is NP hard on them. That sounds weird. Correct? Stare at it for a little bit. Here's a creature. You can use it to answer margins in linear time. But it is NP hard to answer MPE. And MPE is actually easier. Puzzling. Okay. We resolve this in the paper by making the following observation, which again make this creature interesting. Let me show you the picture instead of the theorem. Suppose you have a compiler that takes a probabilistic graphical model like a Bayesian network and give you a corresponding decomposable and smooth AC, right? By the way, when you say probabilistic graphical model as opposed to a Bayesian network, just to give you an insight here, the most abstract way to think of it is a probabilistic graphical model is a set of factors. And what it specifies is the product of these factors. Sometimes you have to normalize. So when you take these factors and multiply them, you get another factor that's not a distribution, you normalize it. That's the most abstract way. So Bayesian networks are that, except that the factors have special meanings. And when I multiply them, I'm always guaranteed to get a factor that represents a distribution. But some other types of probabilistic graphical models, the meaning of the individual factors are not conditional distributions. And when you multiply, you don't necessarily get something normalized. But that's it. So PGM, set of factors, I multiply them, I get a big factor. The observation is, which is the proof is in the paper, is that if you have this box that can take a PGM and give you a decomposable and smooth AC, then that box is powerful enough already to solve MPE. That is, if you are able to get a circuit with these properties using some computational power, that box is already strong enough or powerful enough to solve MPE. It just happens that this box that is capable of solving MPE generated this creature, and this creature, in a sense, stores the answers to marginals, but it doesn't store them for MPE. Right? So one way of thinking about it, as a compiled structure, it actually stored the answers to an exponential number of marginal queries, but it didn't store them for MPEs. But whatever generated this representation is powerful enough to answer MPE for you. So in a sense, there where there's no mystery. Again, which highlights this interesting notion of compiled structures, that they may compile answers to harder queries, but not to easier ones. Okay, this is so this closes this segment. As I said, this is very recent stuff. Someone asked, is this in the book? It's not in the book. Your book came out in 2009. This is 2017. We will make the link to this paper with the video. And the last part of today's lecture, I want to tell you about the last creature, or the last addition to the family of arithmetic circuits. More recent, originally came in 2014, and it is something that we will actually refer to later, at the very least in the very last lecture on structured Bayesian networks. This is very recent work. and in fact, just yesterday, I was in New Orleans for the AAAI conference, and there was a talk by your TA, Jason, on this subject, on his latest results on this. So let me tell you what the last creature is. That's pretty interesting and many branched in so many different ways. Going to the timeline, well, we talked last time and finished at the beginning. Here was this, and then we just talked about the more general picture, including SPNs, and now we're going to talk about something called the PSDD, which can be thought of as using a stronger property of decomposability and stronger property of determinism. It's not going to be a long segment, except that we're going to go back to Boolean circuits. Right? We talked about decomposability, determinism. Going back to Boolean circuits, we'll talk about stronger versions of decomposability and determinism at that level, and then we'll see how those carry over to arithmetic circuits. And I have to say that in all of our treatments so far of these circuits, we only looked at them as an inference tool. We didn't get into learning them. We will talk about some of this later, particularly with respect to PSDDs and so on. So let me do the bit on circuits. And I have to also now tell you that more recently, I guess in NIPS 2016 paper, we switched to using the notation for these circuits by using actual ANDs and OR gates. So this is an NF circuit. Just instead of writing AND and OR, we actually draw them like this. So you've seen this before. This is the circuit, this is the ORs, this is the ANDs, and here are the inputs, either variables or the negations. This, by the way, is a false. You can say, why are you doing this? These things have to be somewhat normalized. You can simplify them, but we work with normalized versions. So you've seen decomposability that says, if you want to visualize it differently, that here's an AND gate. If you look at this subcircuit and that subcircuit, they don't overlap. Right? You've seen determinism. And we said that when decomposability, we have sat in linear time. Okay, so decomposability, we just went over this, and here's determinism visualized differently. Here's the inputs. Red means high and blue low. So in this case, LKPA all high, and if you evaluate the circuit, you see what's going on. Look at every OR, this OR, right? Only one high input. This guy exactly one. This guy no high input, both are low. And so on, right? This is determinism. You've seen this. Okay, so the two things I want to mention here is these two properties that end up playing a role in this last class of arithmetic circuits. One is called structured decomposability. So that's the stronger version of decomposability. And the idea is I want no overlap, but now I want it to adhere to some tree structure. So we call this tree structure a V-tree. It's a binary tree where the leaves are the variables. So this happens to be a balanced V-tree. You could have any other, doesn't matter. But the idea is, when you say, look, this is decomposable, it means they do not overlap. This is not enough. I want this AND gate to map to one of the guys there so that those variables happen to be in the left subtree, and those variables in the right subtree. Right? So it's not just that every AND gate, the guys do not overlap. I want them to be structured, this non-overlap structured according to a tree. So let's look at another example. Look at this guy here. It's an AND gate, no overlap, but you can map it to this guy, L and K. So it's a stronger version of decomposability, right? You have to be able to, I mean, this is a rough description. For every AND gate, you have to map it to one node in the tree structure, right? So that the variables in the left and the variables in the right correspond to those subtrees. What that basically means is stronger property means I can do more things. I can do more things. And one of the things you can do in this case is you can take two circuits and conjoin them now efficiently. You couldn't do that before structured decomposability. The details are not that important, except to realize that it's a stronger version of decomposability. And now I'm going to show you the structured version of determinism that we have here. And by the way, when you have these stronger version of decomposability and structured versions of determinism, you get a type of circuits that we call SDD circuit, or Sentential Decision Diagram circuits. This is the class of Boolean circuits that's based on these properties. Just quickly, this last logical property. If you look at this guy, now we're evaluating it under, again, every variable is true or high. You see, this circuit has this, look at this structure here. There's an OR gate, and there's a bunch of AND gates feeding into it, correct? In fact, this structure kind of recurs in this circuit. It's kind of made up of fragments that look like this and being pasted. And not only that, if you look carefully here, look what's going on. Under this input, look what happened here. This is low, right? This is high, this is low, correct? What does that mean? That means this output here is coming from where? From this guy. I see that? Because this is low, the output of this AND gate must be low. Doesn't matter what I have here. So this is not making it up. It's being killed by this being low. And similarly here, wherever this guy coming is going to be suppressed. You're going to get a low here just because of that. Because this is high and this is an AND gate, whatever color I'm getting on this wire is propagating through the OR gate. So what this portion is doing here is effectively, in this case, selecting that guy. In fact, this is always guaranteed in these circuits, meaning for any input you put, precisely one of these guys will be high and the other two will be low. In this case, this happened to be the high and the other two guys were the low. It could be this is the high, the other must be low. Always guaranteed by the properties of this thing. So this portion is doing what? It's selecting one of these guys to let go through this. It's kind of what we call selector fragment. Do we see that? Now, because of this, what's going to happen here for this OR gate? What's going to happen to the number of high inputs? It's going to be at most 1. Right? If I'm selecting from this guy, if this guy is high, I'm going to get a high, low, low. So there is no way I'm going to get, so low, low, that's going to generate lows. So again, because exactly one of these guys will be high, that's the only guy, the only one that may generate a high input for this OR gate. The point is, you get determinism, but a stronger version of it. Okay? Again, the details for our class do not matter. What matters is, I'm getting decomposability, but stronger version of it, and I'm getting determinism, it's a stronger version of it, and that actually leads to more things. Okay, these kind of Boolean circuits are known as SDD circuits. I know there's a lot of information about these circuits, but I just want you to get the feel of it. And by the way, with these circuits and with an appropriate V-tree, you can actually solve match sat in linear time. So I just want to get this flavor or this notion of you have a Boolean circuit, and if you put enough properties on it, then you can solve certain problems in linear time. Okay, and this is very recent. This is a couple of years ago. Okay, folks. Now let's get to the last type of circuits. Here's where it matters for us. The last type of circuits we're going to talk about is called probabilistic SDDs or PSDDs. I will describe the first syntactically, and then you'll see why they're powerful and pretty interesting, because there's something about these circuits that's very different from the other guys. They're not just based on stronger version of decomposability and determinism, but they give you something that the others do not. The way you get these last type of circuits is by throwing probability distributions on the inputs of OR gates. Okay, here it is. This is now the circuit. Look what happened here. If you look at the OR gate here, it has 3 inputs. So I put a 0.1, 0.3, 0.6. Okay. You can do anything you want here. You just have to add up to 1. This is another OR gate. I put a 0.6, 0.4. Here I happen to put 1, 0, 0.8, 0.2, and so on. Right? You can put these distributions independently of each other. And now you get what we call a PSDD, or a new type of arithmetic circuit. It's tractable in the sense you can do MPE on this as well. margins and so on. But what's missing in all of this, because we're coming to this from a different angle from the others, what does this specify? What is the factor or the distribution that's specified by this creature? And now I'm going to show it to you. And that's basically going to be the gist of these things. Okay. This creature, this Boolean circuit with these numbers attached to it, represent a distribution over the variables that we have, L, K, P, A. Now, here's the part that is new compared to the other ones. How many variables do I have here? 4, correct? How many instantiations? 16. Now look at the distribution. It's not assigning a number to each one of them, correct? It's assigning numbers to a subset of them that add up to 1. Well, what about the grade ones? Why do these guys not have numbers attached to them? You want to guess? Those are the variable instantiations that the circuit evaluates to 0 on. The Boolean circuit itself, think of it as capturing part of the space. So I have 4 variables, 16 instantiations. Some of them, the circuit evaluates to 1 on and some to 0. This creature, this new type of circuit, specifies a distribution only on those variable instantiations that satisfy the circuit. And they end up being very useful in situations where a lot of your Cartesian product or a lot of your space is 0 due to domain constraints and so on. That's where they're mostly used. Right? Now, the semantics is, if a variable instantiation like the first one, 0, 0, 0, if you evaluate it and you get a 0, okay, it's a 0. But where did I get the numbers 6 and 54? And that turns out to be very simple as well. I'll explain it to you. And then that basically specifies this type of circuits. It's very simple. Let's look at the last guy. How did I get the 2.4%? This is when all variables are true. Let's see it. Okay, it's very simple, according to the semantic of this guy. Here's the input. Everything is 1, right? You evaluate the circuit, correct? In this case, red is high and black is low. What happened in this case? We got a 1 at the top. If I got a 0, that means outside my probability space, give it a 0. Now, I got a 1. Determinism, what does determinism tell you? This OR gate will have precisely 1 high input, correct? You follow it. AND gate has a high input. What does that mean? All inputs are high. You follow them. So you start and trace the circuit that's giving you this 1 here. It's going to be this guy, right? You multiply all of the parameters that you encounter along the way. So I'm going down here. I'm hitting a 0.3. If I go this way, that's a 1. Down there, 0.8. And if you go from this side, 0.4, 0.25. You multiply all of these guys, you get this number. That's the probability. This is the semantic of these creatures. And you are guaranteed that if you do this, you get a normalized distribution. Let's go back to this guy. When you put these numbers, all you need to make sure is they're locally normalized, that the numbers on the input of a particular OR gate add up to 1. And then if you do that and you follow this procedure that I just told you, you're guaranteed to get actually a normalized distribution. So these are the PSDDs. They're arithmetic circuits. We say the following. They're arithmetic circuits over structured spaces. What is a structured probability space? If you look at, again, LKPA, the unstructured space is all 16 combinations. The subset of it that we care about is called the structured space. It's a subset of the unstructured space. So this class of circuits is particularly useful when you have a lot of logical constraints or you have distributions that assign a lot of 0 probabilities to things. Any question on this class of circuits? I'm going to tell you one more property they have, which the other two do not have. And that will be the end of it, which will make them even relevant to doing inference. Yes? What you're saying, what do these guys add? Right. So I will tell you in a second an operation you can do on this in polynomial time that you cannot do on the others. But when I tell you, give me an instantiation and let's evaluate this guy, and if it ends up being a 0, then this is semantics. This is not how you use it. This is trying to explain the meaning of these things. So, but are we clear on the semantics? So if I show you one of these creatures and I say, what is the distribution? It specifies, we know how to do that, right? Okay. One of the things you can do with these that are enabled by these guys, which are not enabled by the others. The first I already mentioned that you can use them to induce distribution over structured spaces. The other is the following. We will use them to take a probabilistic graphical model like a Bayesian network and convert it to one of these guys, but using a different method than what we did last time. And we will capitalize on the property they have. First observation. Here's a factor. A factor is not a distribution, right? These circuits represent distributions. So here's the first observation. You can think of a factor as a distribution plus a number, correct? You add up all of these numbers, you get a 7, right? So if you normalize, you get a distribution, but you keep the number 7 around, so you can recover the factor back, correct? Okay, so now what I'm going to do is I'm going to use these circuits to represent factors, but I have to keep a number with them. So a PSDD distribution and the number. That's a factor, okay? Okay, simple observation. Second observation, which you already know. If you have a probabilistic graphical model like a Bayesian network, here's an example. It's made up of these factors, 5 of them. I can get the global distribution or factor specified by this model by doing what? By multiplying these guys, correct? We know that. Okay. Now, you will not do this if these factors were in tabular form because you're going to blow up. But a game that people have been playing for a long time was that instead of representing these factors tabularly, I represent them using more compact notation. So I will use a PSDD to represent this factor, a PSDD to represent that factor, and so on. Okay? And then what do? I multiply these guys to get one big PSDD for the whole thing. This is an old game in probabilistic inference, and people have proposed many different ways to represent these particular factors. Here's some examples from the past. So now we're doing PSDDs for that. But now where's the caveat in all of this? To play this game, you have to be able to do what? You have to be able to multiply. That is, I give you a PSDD that represents one factor and a PSDD that represents another factor. We know what factor multiplication is, right? So I wanted to generate a PSDD that represents their product. Can you do that efficiently? And the key thing that you can do with these and you can do with the others is multiplication can be done actually in quadratic time. So here's the theorem. Just to visualize first before I give you the theorem, here's the factor. Here's a factor. I want to multiply. You guys know what this is. I happen to have this represented as a PSDD and a number, PSDD and a number. I multiply them. I want that. And here's the key theorem. If you have two PSDDs, one have size S1 and the other has size S2, then I can actually do the multiplication and give you the output in this quadratic time, polynomial. And provably you cannot do the other, you cannot do multiplication efficiently on the other two types. That's enabled by the stronger properties that these circuits have. But to tell you the truth, this is in a way a secondary result of these things. The main advantage, and you'll see it later, is the fact that they end up defining a distribution over only a subset of the Cartesian product of the variables. And that ends up being a big deal. In certain applications, most of those instantiations will vanish. So you need a principled way of generating a distribution over the subset of the space. Just a couple more remarks on this, and we're basically done. This looks good, but then someone says, "Wait a minute! All you're telling me is that each one of these is okay. That is, if you take this and that and multiply it, that's quadratic. That's good. But what when you cascade these and do a whole bunch of them, would you blow up in that case, right? Because If every step is quadratic, is good, but if you have enough of them, you could blow up. You get the following guarantee. You get the following guarantee that, at least for graphical models, you can play this game without being worse than 3 width, right? So this is the classical baseline everybody has to kind of meet. So if you have a graphical model with n variables and a 3 width W, we can construct a PSDD in the usual guarantee, right? So it's not going to be worse than what we've seen before, but that's again not interesting. This is interesting only to say, okay, I can be worse, but you want to be much better than that. And in fact, with the you can be with logical constraints, you can actually be significantly better. This is also very recent, by the way. This is this results about multiplying these circuits. This is last year in NIPS 2016. This is also work of Jason, our TA, who's doing his PhD on this subject. Let me mention also, we'll put also the link for this paper. It also investigates summing out. Because again, if you think of these circuits as representing factors, then it's meaningful to talk about, can I sum out a variable? Can I multiply to just the usual factor operations? And this is what I just mentioned, that you cannot multiply with these guys, but you can with those. I will leave some out to the paper. You can do and not do certain things, so it's blank. It's left blank for the curious to consult the paper on this particular subject. We're done. I want to just quickly give you a mental map of what happened here. From a very practical and concrete point of view, what you have is 3 particular types of arithmetic circuits. Right? These are circuit representations of distributions or factors. There is the first type, the traditional one from a while back that we discussed at length last time, and today we discussed 2 more, right? The SPNs, which have weaker properties. They could be exponentially more succinct, but then you lose certain abilities or certain tractability when you work with them. And then there is the PSDDs, which are stronger properties. They give you more, right? But you also expect them to be less succinct. The PSDDs will come back later because they excel when you have this notion of domain constraints or Boolean constraints. In fact, one of their main uses is when I learn models from both data and knowledge. So we'll come back to that. But orthogonal to this concrete and practical side of things, that is, I have type 1, type 2, type 3 circuits. Concrete to all of this, or parallel to all of this, is this new understanding of circuits that we portrayed. That is, the notion of a circuit computing a factor, and how if you add properties on that circuit, then the circuit starts giving you more tractability and so on. So in particular, we characterized the properties of smoothness, decomposability and determinism, and visualized it. And this closes this segment of this part on exact inference. We will be starting on approximate inference next. It's going to be a relatively, maybe not as long of a portion, and then we go into learning after that. So thank you, and I will see you on Thursday.